Hello everyone. Today we will present and discuss the paper entitled Meta-Learning with Differentiable Convex Optimization. So the outline of the presentation will be as follows. We will first discuss the problem state of meta-learning and the approach overview that this paper takes into consideration, and to go to the details of this approach, the meta-learning with convex-based learner is the base of this paper. And we will see the experiments done and the result, and finally the conclusion. So after this presentation, we can discuss. Anyone have any question about the presentation point? We can discuss it, and we will see some code that implements this paper on the experiments done with the paper and on another database that I had prepared. So let's start. Let's go directly to the problem of meta-learning in general, and that already taken in this paper. So meta-learning, the approach for few-shot learning, rely on simple-based learning such as nearest neighbor classifier. In general, there is a core of meta-learning model, embedded model, and after that there's a head or some base classifier that already or in most cases chosen to be nearest neighbor classifiers in general. However, in this paper, we will see another type of head, is SVM and Convict-based classifier. So, the objective of this paper is to learn feature embedding that generalize well under a linear classification rule for novel categories. So it is also not the objective of only this paper. It is a hot topic in machine learning today, which is the meta-learning and the few-shot learning. So, meta-learning approach in general for few-shot learning aim to minimize the generalization error across a distribution of tasks, of course, sampled from the same distribution. In this image, you can see that it is image from MAML, model agnostic meta-learning for fast adaptation of deep neural networks. As you see, the meta-learning parameters they are trying to generalize both parameters in order to adapt for several specific tasks. And this is done according to the techniques or the approach done by MAML. However, in each approach, there is a different model to take this problem. So let's go directly to the approach done by this paper. As you see here, this is the approach overview. You can see an overview of the model approach, schematic illustration of the meta opnet, as they call it, which is here in this case a three-way or three classes. And in here you can see the parameter of feature embedding model. So the embedding of training examples. After that, there is a head of, here in this case, it is SVM. However, you can find any classifier which can be a convex problem of optimization classifier that could replace SVM, and we will see in the next slide. And after that, in this stage, all this stage is used for embedding learning. So all this stage for embedded learning. After that, they use the model to find classification for novel categories that are not already from the learning categories, from the model agent. So After that, what they have, they test the model on novel categories and they get the result. This is the approach used in this case. So they took into consideration 2 points, and the SVM head classifier is a convex optimizer problem. So in this case, they take advantage of convex optimization problem to enhance the computational efficiency and the time needed to learn the model. So this is the main, let's say, added value that they added to the literature, the convex optimization. So let's go to the how they solve it with the convex optimization. Meta learning with convex-based learner. So the base learner is here a convex problem. How this problem can be formulated as follows. This is a general formulation. Let's say that we have two training sets, one training set and one test set. Let's say X for the data, Y for the labels. For example, the goal is to um, learn a base learner A, which is here in this case, we have to estimate the parameter theta of the predictor Y. So, of course, we have the test set, which is different from the learning set, however, it's from the same distribution, using an embedding model F parameterized by phi. So this is the minimizing the empirical loss over time trained data. Here you can see this is the problem, optimization problem. You have to minimize this loss function. And R here is a regularization parameter. This is a general model. This is a general problem. And here we are trying to apply it on a collection of tasks, not on one task. So, for example, if we have to use a collection of tasks, here tasks from 1 to I, let's say, and here we denote by T is the tasks we have that take into account as a parameter the training dataset and the test dataset. And in this case, the same model can be applied. However, here we have different tasks, which mean we have to minimize phi over an expectation of these tasks. So because we have multitask. So how to deal with this problem? It is a context-based learner. For example, if we consider SVM, context linear classifier, and the Kalmer and Singer formulation of multi-class SVM in general is at this equation 3. You can see here that we have to minimize over the WK, which is the weight of the parameters of the classes, where K is the K in the class index. And here we have the epsilon, which is this is a regularization parameter subjected to a set of inequalities. So this is a general Kalmer and Singer formulation of the multi-class SVM, if we consider an SVM head. However, the paper considers a general linear classifier as a head. So they put this as an example. They take advantage of 2 points from convex-based learner. Because they use convex-based learner, they think that they can efficiently compute the optimum point by taking into consideration that convex-based learner we can make a dual formation of the problem, just make it easier to be calculated. And here they transform the problem into a quadratic program, QP, which is already had been implemented by this reference. And there is a implementation of the differentiable GPU-based quadratic problem. So we're using formulation of and Amos and Coulter. So it is already been done by this reference. They implement the quadratic problem and they add it as for the SVM, which run efficiently compared to other near neighbor classifiers. So the next point that they take advantage of is the gradient of the SVM object. So we have in theorem the objective of SVM is convex and has a unique optimum because it is a convex problem. This allows for the use of implicit function theorem on the optimality KKT condition, which is a Karush-Cohen conditions to obtain the necessary gradient. This is a general convex optimization problem which can be formulated here. Here is the Lagrangian formulation where Q, lambda, V, Z are the parameters which needed to be optimized. And this is an optimization point. The optimum point equals 0 when we differentiate over those parameters. And so this theorem can be solved based on this Jacobian equation here. So this is in general, if we have to just make sure that we understand what is the added value of this paper, they take advantage of two apart from the convex phase optimizer, which is the gradient of the SVM objectives, and they take advantage of the dual formulation of the problem. They transform it to quadratic problem, and because there is already a solution, an efficient time solution for a quadratic problem, which is already implemented, they make the computation in a very efficient time, and we will see that in the result. So this is the problem or the added value of the paper and how they deal with the convex-based learner. So let's go to the experiment. So how did they learn the meta-learning model? First, as the network, I mean here by the network is the core network, which is before the part before the head or the classifier. They use, in general, they use ResNet 12 network. They also use another networks for comparison, but here in general, the best models they obtain when they use ResNet 12 network for meta-learning setup. And as an optimizer of this network, they use SGD optimizer with the Nernst momentum of 0.9 weight of decay of 0.0005. For meta training shots, so in the learning shots, we have training shots and the validation shots. For when they use prototypical network, they match the meta training shot to meta testing shot. They use the same number of training for training and testing shots. When they use SVM and rigid regression RR here in this paper, they observe that keeping meta learning shot higher than meta testing shot leads to better test accuracy. So for the base learner, as we say that they use linear classifier and they use quadratic programming solver to solve the option. So those are the setup of the experiment. They set the experiment as this in this technique. So how did they obtain the results? We will go directly to the result to see what they do. I think here I need to use the slide here. So in general, they apply their approach on 4 data sets. The first 2 data sets are derived from ImageNet. the first one called mini ImageNet and tired ImageNet. So they compare a lot of models to the model, and you will see the result here. You can see that meta-learning LSTM with a backbone 46, 46, 46 is above the other layers, and with one shot and 5 shots. So the mini ImageNet 5 shot here, the mini and 1 shot, the tired ImageNet with 1 shot and 5 shots, and these are the models they use to compare. As you can see, the best models here are in the bottom of this slide. You can see that here the meta-learning LSTM matching networks. This is for the backbone. They use this technique. Prototypical network from those reference. If you want to know the details of the reference, you have to go to the paper, because I didn't mention all the references in this slide, just the basic ones. So they compare it to MAML, 32, 32, 32. They compare it to relational network, R2D, and Suction, ProNet. And if you want to go directly to the result, they make a good result. And you can see that the best results are when they add the meta-opnet, their network, with a rigid regression head. So in the first part is the core network, and the second part is for the head, classifier head. So as we see that the backbone is ARIthmet 12, and here they apply rigid regression and SVM trained on validation set. So those are their results. Of course, you can see that they do better on tired ImageNet, and you can see here that they apply almost 46% on the first shot. Only one shot, they apply 46 accuracy, plus or minus 0.62. On 5 shots, they reach 80%, which is better than all the models when they use SVM trained on validation set. On trained ImageNet, they obtain 65 with SVM head, 66 with RR head. When you go to 5 shots, you can see that the best result is when they use the meta-opnet with SVM head. So this is a comparison. You can see that all of these are considered a hot topic on the literature. They are a good network, like MAML, like relational network, and they outperform it with their network. Okay, so let's go to see the comparison of this work on the CFAR network. So on the CFAR network, as you see, CFAR, there is two derivatives of this data set, which is CFAR FS and CFAR F100. For the CFAR FS, they also the same setup, 1 shot and 5 shot. For FC100, they also use 1 shot, 5 shot, and they also compare it to MAML, prototypical network, relational network, R2D, data, meta-opnet with head regression, rigid regression, meta-opnet with SVM, and meta-opnet with SVM trained on validation set. And you can see that on CFAR FS, they reach 72% with plus or minus 0.67, which is better than MAML and prototypical network. Also, you can see on FC 100 with 1 shot and 5 shots, they reach with 5 shots 62%. Okay, so comparing, let's compare now. They make some experiment to compare the classifiers head. So they just start to change the classifier's head with the model used. Here we have two groups. The first group contain models, prototypical network, meta-opnet. These are the groups of embedding network. The first group, 4-layer convolutional network. The second group for embedded network as ResNet 12 with a feature dimension of the first one 1,600, the second one 16,000. So let's go to the result on mini ImageNet and on Fire ImageNet. You can see when we use the embedding model with a prototypical network as a classifier head, we reach as an accuracy on one shot 53.4, and when we use the OptNet RR as a classifier head, we reach approximately 53.23 and 52.82. So this is on mini ImageNet. The result on Fired ImageNet is pretty better on the one shot. On the 5 shot, it's the same. So, however, if we have to compare those two groups, ResNet embedding is embedding model make better results. You can see when we just change the embedding or the core embedding model, we can see that with prototypical network 59 compared to 53 is a very good added value here. So, and we can see that the best model applied is when we apply as an embedding model the ResNet 12 and as the classifier the meta-opnet SVM. So I think here we can see that the optimum model on the two datasets or on the 4 datasets is the ResNet 12 with a head of meta-opnet SVM. And here they make some experiments to see the accuracy compared to 1 shot and 5 shots. We can see that on both datasets, mini ImageNet and Fired ImageNet, the meta-opnet SVM with let's say the orange line, it was 5 shots here, is better than prototypical network. And we can see even it's on 1 shot or on 5 shots, it is the same. And we can see that OpNet with SVM 5 shot or OpNet with SVM 1 shot make better accuracy on both networks and even on 1 shot or on 5 shots. In conclusion, we can see here that we have 3 points and the future work, the optimization condition. On the optimization condition, the dual functionality of KKP parameter foundations can be exploited to enable computational and memory efficient meta-learning. This is the first point. Classifier point, the linear classifier offer better generalization than nearest neighbor, and we see that on the result. So they see that the linear classifier offers better generalization than nearest neighbor classifier at modest increase in computational cost. On the embedding, the regularized linear model allows significant higher embedding. We see that also. For future work, they speak about work to explore other convex-based learners such as kernel SVM. So I will take some questions on the presentation. I will go direct to the implementation code.
Hi, Moz. This is Amit here. Ahmad, sorry.
Yeah.
Can you hear me?
Yeah, I can hear you.
So, okay, it's a very basic question, but I don't have a clarity on it. What exactly is meta learning?
Yeah. Meta-learning is when you think of transfer learning from a model to a model, or I don't know if you're already familiar with pre-trained model.
Yes, yes, yes. I am. Yeah.
So if you want to transfer this learning from one model to another, uh, you have to think of this technique called meta-learning. You have to learn generalized parameters that can be used on another tasks. And in general, the hot topic today is to learn these parameters with a few shots. And this is the hot topic of the today literature on machine learning, the transferability and the few shot learning using this concept called meta learning. So it is not to learn to learn the parameter from other models, to transfer those parameters and to learn for a specific task.
Okay. So it's also a transfer learning, but only you don't take the whole model, but take the parameters which are required for our task.
Yeah, and it is different from sometimes when you learn meta learning, maybe there is parameters from the model itself. Maybe there are parameters, it's a hyper parameters that are like learning rate, like something like that. So meta learning does not consider just the parameter of the model, like the weights and something like that. It also can be considered other parameters like hyper parameters.
Okay.
Hi, Ahmad.
Thank you.
Okay.
Hello, can you hear me?
Yeah.
Yeah, is it the same as self-supervised learning? Because I've just come across self-supervised learning and it sounds like a very similar to that.
I didn't. I'm not very familiar with self-supervised. I didn't know if maybe I know it, but I didn't know the label what self-supervised learning. Like when you teach yourself from what you already had learned. It is not like that. I didn't think it's like that. If I understand the concept of self and supervised learning, because you have a large model like let's say ResNet 34, and you train it on a large set of classes which are different, and then you will just start to adapt it or to generalize those parameters to learn new classes, which may not be part of the learned classes at the first point. You get the idea? So
Yeah, okay.
So maybe you can use classes that are not seen for the model before, and
Okay.
you will take advantage of the features learned from the core model, or let's say call it core model or backbone model, and sometime you can just learn, freeze the model and learn just the last parts of the model near to the output to make use of the transfer learning in this.
Okay. So are you saying like it's like this you can train the model, like you can use a pre-trained model from a different domain, like data in a different domain, and then use the same parameters of weights to
Yes, it's like
classification.
that.
Okay.
Yeah. You can use data from different domains, from different classes, and then you can just train the head network on specific or novel classes, like that.
Okay.
And you take advantage of the pre-learned parameters.
Okay. Thank you.
Okay. Is there other questions? Okay, let's go to the implementation of this code, and maybe you can have an idea on how to implement such a model, or how can you use such a model on your work or on your data set. So here, as you see, the training file, there's a function for one hot just for encoding. There's a model where they construct the model. There's the get data set where they construct the what we call the few-shot data loader, and the data set. They have some processing on the data set, like transformation or something like that. So here are parts just for command line, and you can go just here. They load the data set. When they load the data set, they take into consideration number of novel classes and number of experiments from base classes. So they divide the classes into novel classes and base classes. And also they divide the data loading as a validation and as a training set. Did you see my screen?
No, I only see the PowerPoint presentation still.
Okay, I have to share the whole screen. Now,
Yeah, it looks good.
did you see the screen?
Yes.
Okay, so this is the training file. We have here the we get the model. We have a function that get the model. We have a function that get the data loader, and this is an art parse that to use this as an application from the command line. And they load the model. The model you can specify how much novel classes you want to use, how much base classes you want to use. So the data set is divided into novel classes and into base classes. And let's go directly to the training epochs. Here we can start. Here are the epochs. At each epoch, there is a training stage. After the training stage, there is a validation stage within each epoch. So let's go into one of these epochs. Here you can see that we get the training data loader to get to load data from training set, which also contain novel and base classes. As you see here, when I'm saying embedding, I'm speaking about the embedding model. Okay, and the embedding query is the result of the embedding model, and they get the embedding model, and they use one of them using the novel and one of them using the base data set. And when I'm saying here the logic query, it is the head, is the model of the head, which is in general SVM, or other models. They use rigid regression and other models as a class head. So within the same training loop, you can see that here we are making meta training, because there is a difference between the meta training, meta learning, and on the test, there's just a test on the whole model. So this epoch on default runs for 60 epoch, and you can see here that we are training both models on the same epoch. So what we have here, after training the model, we can see here run the best parameters or the best model. Here we start the evaluation. We evaluate on the test on the validation set here. Also, we have we load the embedding support, the embedding query, and the lattice query. We get the losses, the accuracy. If we have better model, we will save it. So at each epoch, we will compare the models. The best model will be saved as the best model here. This is the training epoch. As you can see here, I think the optimizer that is used is an SVD optimizer. Well, it's here, SVD optimizer, sorry. So the optimizer used here is an SVD optimizer that takes the parameter of the embedding model and takes the parameter of the head model with a learning rate start 0.1. Okay, and there is multi-step for the learning rate. I didn't go into detail, but you can see that the optimizer working on both parameters of the embedding and the head at the same time, as it is a layer from the whole model. Okay. So they, however, they create the two models in a separate way. They didn't merge the model into one model. If you go to the test set, you can see here that the same thing happened. They validate the set on the test data set, which is a novel class compared to the other classes. And as you see, they load the data into the embedding support and into the logisticity class logic of the SVM. Let's say if it is SVM, they just make optimization for 3 files only. All else they use make optimization just for the better result, for the best result. And let's go to the after applying this on the data set, you can see here the result. I run the command, which is train for 5 shots with a head, a rich head, RR head, on a network base called ResNet, on the dataset called C4FF. It's very easy to use the command line. And after that, the result I get is as follows. You can see with just 3 training epochs, you can see here, we get a here accuracy of 64. Okay, and after this is the first epoch, the second epoch, with the third epoch, we get an accuracy of 84. It is a very promising result, just 3 epochs. And after I test it, I find it is 64.52. Here 64.52 on novel categories. So the because the network didn't see those categories before training or within training, so the accuracy, of course, degrades to 64.52. And I think the results are promising. And however, the problem that I faced during this applying these codes or applying it on our dataset, which is related to our project on emotion detection. I have applied it. However, the problem is that you have to train some of the classes within the SVM. Let's say here I use an SVM network on the dataset. We use our dataset, however, we just put the name of the dataset in the literature, not to replace all the names in the code, but here it's our data set. And the problem we get is that we didn't have a lot of classes because ImageNet, maybe some, or FC100, there is 100 class. However, here when there is just a little amount of classes, we have some problem at this point. And we get a primary result. I don't know if it is just here or yes. We get a primary result of 51% on our data set. So just with, I think, 3 or, yeah, it is exactly 3 training epochs to get this accuracy. And it is considered novel. Those at both sides, it's considered novel. Our class is considered novel. So I think with just 5 to 6, we can go more with more accuracy. So anybody had any question about what I had presented today? I am ready to answer. And I can, the code is already shared on GitHub for this paper. And from my point of view, I already implemented. Anybody has any question about the code, I can answer it.
I guess just to make sure that I understood everything correctly, what this is doing is it's taking kind of like a convolutional neural network, but just like the first part where it just creates an embedding. So it's creating an embedding from images into like basically a lower dimensional space. And then from that, it's applying like a support vector machine or ridge regression in order to do classification.
Yeah, linear classifier, yes, that's right.
Yeah. So I guess during the training stage, is it training the embedding network? Is it training the support vector machine, or is it trying to train both together?
Yeah, they train it together. They train together, and this is the drawback, I think. And most of the papers do that. If you go to MAML, even I think not if I have the so this is the point they use in MAML. Let's say you have the general embedding feature, and then you start to when you are in the what they call it the meta training, they train also the head class to make the general parameters good enough for the head class or the base class, what we call it. So they train it with each other, and then after that they apply new novel data sets to this model. However, in some cases, or in most cases, they retrain just the head model on a specific novel data set. So it's like that the head model is also pre-trained.
So the support vector machine is also pre-trained?
Yeah, the parameters are the parameter of the SVM are pre-trained, yeah, and then they will load those parameters when they want to test the model. Yeah.
Does it take small steps for both training the SVM and the neural network? Or does it take the support vector machine all the way and then try to tweak the neural network to kind of like make it a little bit easier for the SVM?
And you mean when they on the meta training?
Yes.
They compare the training of the linear classifier compared to other networks, and they said that they already have some results on the training time. They said that because when training linear classifier, there is a less parameter than the features you should train on prototypical network, for example. So they think that learning an SVM parameter is most time effective. in general. But to answer your question, they are trained, which is other in the same optimizer. So the optimizer is using torch optimizer. Let's say in this implementation, you can load to optimize parameters from different layers of the network. As you know, I will show you on the same chart here. For example, here it is a torch optimizer SGD, and the parameter they took from the embedding, and then the parameter they took from the head. You see the you can see the screen. Can you see the screen?
Oh, yes.
So you can see that the optimizer here is working on both, and they take into consideration that the SVM, which is the head here, for example, SVM, maybe another linear classifier, is like a layer in the network. So how much it takes to train the embedding, and this one, I didn't have a comparison in time, but it is easy to compare it. It's very easy. But I didn't have exact time record about each training time of each layer. Here they are considering it like a layer, as you see.
Okay, that makes sense. Thank you.
Okay. So I think, is there another other question on the code, on the implementation, or on the paper? I think we are done for today, and thank you for your attention, and I hope we can take advantage of this implementation or of this paper to improve our work. Thank you very much.